All right. So right now I am doing this from the phone because the computer is not wanting to open up Zoom. Hopefully you can hear me. You can at least see my lovely mug, or what's not covered by the mask here. Hey, bird cool. It's gonna slide. Oh. Situation. All right, give me a second here. I'm trying to figure out, see if there's something I can't do to get this to work. Can I try to restore previous versions? Oh, there's no previous versions to restore. Fantastic. I'm not going to be able to actually. I think it's administrator. I don't get administrative privileges on this computer. Oh. Sorry, I'm trying to think about if there's anything I can try to do with my limited privileges on here. I'm going to try to will allow me to, I doubt it. We can download and install the more recent version. Oh, no, it's just popping up. All right, great. And I can't restart this computer, right? Yeah, no, that's not going to get me any good. That's all I have privileges to do. Yeah. I hate that. All right. I know all the plugs are there's one thing I can unplug, but it's definitely not for the computer. It's for something else. And I don't want to unplug the projecting system and all that other crap and have that. So I'm not gonna unplug things. So let's see here. So let me at least pull up slides here for stuff. Oh no, of course I haven't plugged in my flash drive yet as I'm trying to resolve this. Oh, did it? Yeah. Let's see. Yeah, so I log into Canvas. So there's a question right now about the. Yeah, sorry. Right. I assume people hear me, right? Oh, my microphone is muted. No.
We can hear you.
Oh, what? My phone is lying to me. All right, fantastic. This is great. All right, so let's see if I can figure out something I can do here. Course. Quizzes. Random quizzes from semesters here. Expert one is what I called it, right? Preview. It's that third question you said. Yeah, question. Oh, 3. Yeah, I'm looking at question 4. What do you mean? What is the rate law for the following mechanisms? Oh, huh. Yeah, I was not even thinking about that. I was just thinking, yeah, shoot. I should have just asked what is the change in concentration of I as a function of time is what I should have written. All right. Yeah. So question 3. I'll go through and just make. Can I change it? Okay. Yeah. So there's a question about question 2, and then any other questions about the questions on the quiz here. Let's see how I can pull up chat on my phone. For those who are chatting, here we go. Chat. Number 3. Oh yeah, so number 3, yeah, it was me. Oh, well, I'll do the question I should have asked. Wasn't paying attention when writing it about where we were in the lecture. So yeah, number 3, I apologize, was not one we'd gotten to yet. So 3 and 2. Okay. Let's see how I'm going to do this. Maybe no idea how much people are able to like see if I were to do things on the board. I'm just trying to think how I can work out problems where people can see it. So let's see. Try something here. Oh, okay, not that. Where is thing for the screen? Turn the chalkboard lights on. Now, forget.
I think it was a little bit better with the chalkboard lights off.
Oh, was it? All right, well, I'm turning off the projector screen as I want to do something on the chalkboard. Oh, that's right. I forgot. This room is manual. It's CHEM 100 that's got the automated version. All right. So, all right, so let me just. Can people on Zoom see that better now?
Yes.
Or now? Is it better with the lights on or off? I guess in class as well.
Looks fine how it is now.
So off is fine or on is better?
Yeah, I can see good.
All right. Well, then we're going with the lights off here. Okay. So I told the projector to put a blank screen, but yet it's still. Give me some light, whatever. All right. So question 2 on the quiz. Okay, so we're given the half-life. So the idea is you got like carbon-14 decay. Okay, nitrogen has a half-life of, what do they say, 34,000 years. Okay. And the question is you take a small sample of a fossil and determine that in that small sample, 35% of the carbon has decayed. Okay. And the question is, how old is your fossil? Okay. So we know that 35% has decayed, which means that our current concentration is equal to, well, hopefully I did that right, 0.65 of the initial concentration. Now I'm already thinking in my head that I didn't do 0.65 and I maybe did 0.75. I don't know. I hope I did 0.65. But that is your current concentration is 0.65 of the initial, right? Because 35% has decayed means that 35% has gone away, and what remains is the 65%. So the current concentration is 65%. Okay, and that's your half-life. So then all we need to do is just plug in for our equation here. I'm going to write an ln of 0.65 E naught over E naught. A naught here is your carbon-14, right? Doesn't really matter, right? It's equal to minus K times time. Well, the rate constant K, right, is related with the half-life through the equation ln of 2 over T 1/2. Okay. And so plugging all that in, you can see on the left here, right? Plugging all that in, you basically get that the time, the age of your material is equal to natural log 0.65 over natural log of 2, the minus sign, right? Because natural log of 0.65 is going to be a negative number, so you better need that minus sign so your time is not negative. And then you multiply by the half-life, right? Or I guess plugging in for that, right, is 34,000 years. Okay. And so plugging in those numbers should hopefully give you the answer that is on the quiz, but if people say it doesn't, then that sucks.
It gives you 21,130 years, which is not the answer.
All right. I will check that in my office. Likely, like I said, as I'm writing this out, I think in my head I went 0.75 here would be my guess. And so, but I'll see. You know, but yeah, so that should give you the right answer, but apparently it doesn't. So I will fix that on the quiz. So for question 3 on that quiz, and for those who didn't have me last semester doing these things, this is a normal Monday. These quizzes I create randomly, very quickly, late at night. Don't always work out so well. Right, so the third question, what I had was A plus B going to I, as you know, K1, then I plus I going to, I don't know if I called it C or D or what, so we'll say C, K2, right? And I asked, what's the rate law for this using the steady state approximation? Okay. That question is a question for this week, not so much last week. What I should have just asked is, what is DI dt? So I did this question as kind of a reminder for people that, hey, right, if I'm going to look at what di dt is here, right, I would have K1 A B, and then you need to remember the fact that we then have minus 2 K2 I squared, right? That this factor 2 was here. That was kind of the point when I created that problem, was to make sure we kind of understood, hey, there's this factor 2 that needs to be there when writing out what di dt is. But I just asked kind of the wrong question. I created the quiz around the time where I was recording lecture videos for this week, and so steady state approximation is in my head, and I forgot that we hadn't actually done that yet. So I apologize for that. So I'll modify. I mean, question 3 I'll just make worth 0 points, and then I'll fix question 2. So, other questions about the quiz? Yeah.
So that one specifically, I kind of toiled on for a little bit, just because a couple of the terms were kind of, you wanted to grab them, right? Is there any way, I don't know if there's time, I wanted to maybe go through some of the other answers and see why those didn't work? Like the other options, like there was a Ki squared, and then there was one that was like K1 over 2.
Yeah, so I mean, so to get those answers requires stuff that we're going to talk about today.
I see.
So basically, I just should have never asked that question.
Sorry, I got it right miraculously, but yeah.
But yeah, so yeah. Any other kind of questions?
Yeah, I had one about the quiz real quick.
Yep.
Is just to make sure, are all like radioactive decay processes, are they first order reactions?
Basically, yes. I'm trying to think. I'm sure. Like, so I guess a radioactive decay. If you're given the term decay, then yes, that should always be first order process. If it, Nuclear reactions aren't always first order, right? I mean, you think of particle accelerators and things like that, right? Those are not first order processes, right? Those are, you have typically collisions. I mean, some of them are. Some of them you just speed something up really hard and then hit it against the wall. So I guess that's sort of first order or whatever type of thing. But you know, certain things that take place in, say, a particle accelerator, you're colliding two nuclei together and things like that, right? And so that's second order, right? That's requiring you know, collision between two stuff, so it's not going to be a first order type process. But yeah, but if it's a nuclear decay, then yeah, those decays are always first order. But yeah, nuclear reactions aren't necessarily always first order. But nuclear decay should be, yeah.
Okay, and then one of the other things was on the homework, there was a problem that has the reaction 2A going to P, and it says that as a first order reaction, which I mean, usually when you see the 2, we would think like it could be a second order or something. So when you're deriving the integrated rate law for a first order one, will you have to set up the expression different, like -1/2 dA over dt is equal to that corresponding rate law, and then it'll have a factor of 2 in the exponent?
Let me pull up the homework real quick just so I see what you're talking about here.
Yeah, it just, it didn't count right.
Which number, if you don't mind telling me real quick?
I think it's problem 9.
It was a decimal.
9, the rate constant for the first order decomposition of compound A, reaction 2A going to P is, okay, so it's 2A going, okay. Yeah, so in that problem, you're told, so the reaction, right? So this is, again, a difference between a reaction, an overall reaction and an elementary reaction, things like that, right? So the idea here is you have this chemical reaction that has A plus A going to P, but you're told that the overall, you know, rate law for this, you know, is first order in A, okay? And so, yeah, so in terms of integrated rate law and things like that, right, I guess the trick here, and I guess, I mean, whatever, right, it is just keeping track of the fact that you have 2A going to P in the reaction, and that rate of the reaction relate with the rate of change of A because of that factor of 2 stoichiometric coefficient, right? So this, you know, so you'll get things that look almost exactly identical to an integrated rate law and things like that, but there should be something that's slightly different because the stoichiometric coefficient is 2.
Okay, but you would, yeah, you would still assume though that the actual rate law that you're setting the differential equal to would just be like KRA, like it's stating it's a first order one. Okay,
Yeah,
but then you just need the
first order,
stoichiometric.
just the rate constant times concentration of A. Yeah.
Okay, makes sense. Thank you.
Good. Any other questions about anything before we get going today?
Question 4. Yeah,
Oh.
we're here debating it, because I didn't get that right either, and I wanted to do it twice.
All right, question 4 on the quiz. All right. Yes. All right, question 4 is, what is the activation energy for reaction where the rate constant is from 215 to 467, temperature increases from 250 to 310. Okay. So again, I'll set this up and then, you know, say I will double check the math, and, you know, after class, and if somehow I plug in things wrong, I will obviously fix it, right? But so in this problem, we're looking at a temperature dependence of the rate constant. So we have the natural log of K2 over K1 equals to minus A over R times 1 over T2 minus 1 over T1, right? It's basically the problem, right? So it's just plugging things in, okay? So it's the natural log. The numbers you're given is 467, 215. And this is minus the activation energy you're looking for, 8.314, right? Your ideal gas constant in joules per Kelvin mole. And then the temperature, 310 minus 1 over 250.
So there's my question.
Yep.
In the example you gave us last week, how it was set up is it went T1 minus T2, I believe.
Yeah, I know. I keep on swap. So basically, it's just minus sign, right? So there's maybe there's a purple cup here, right? Oh, can't keep it.
And so no matter what, we just want that temperature factor to be negative. That's all it is.
Well, I mean, yeah, I mean, it's like, so there's this minus sign out here, and I have T2 minus T1. If I got rid of the minus sign, it would be T1 minus T2.
Ah, that's my confusion. Okay.
Yeah, sorry.
No problem.
No, that's just,
Easy trick.
well, yeah, I just, I write this, I'm just gonna, I should just change the slides in the very beginning. You know, like, and while doing stuff, I just think back to, like, again, in 3330, we have lots of equations like this form. Something like delta H, right, over R, EA over R, 1 over temperature differences, natural log of something, right? Like this equation pops up many different times, right? And, you know, typically written with a negative and then final minus initial, you know, final over initial type of thing, right? So, but I, for some reason, have, you know, in the slides put, like drag that negative sign through and wrote it that way. And so, yeah, so I apologize for the confusion.
That was definitely my mistake. You definitely said that last week. You know, this is a minus sign, and then we make this term the negative. You know, the property is -1. I remember you talking about it.
Yeah.
So the easy mistake I made, but that cleared it up. So now I completely understand the concept. So
Okay.
no worries.
All right. So hopefully the numbers I had for this actually worked out. But some people saying yes, they got. As long as you got the same answer as me, then my numbers obviously were correct, right? Yeah. Any other questions before we kind of get going today? Steady state. Let me check the full chat here on my phone. Nothing on the chat. Fantastic. Hello. All right. Okay. So let's pull the slides back up. Talk about the steady state approximation here. Put it back on. All right. So see how well you guys are able to just a second here. Middle. So let's and push it out. There we go. More broad view. All right, so that's the best I can do. Again, I can't really do a share screen, so but hopefully you can see this. Otherwise, you know, the lecture slides are posted online, and you can always, you know, kind of go through the slides, you know, both slides on your computer and just listen to what I'm saying and maybe look at me point at some crap or whatever on the screen. But yeah, I apologize. Hopefully this stuff will be fixed by Wednesday. I'll make sure to contact ITAC about it immediately so they can get someone to fix this. But, all right. So the steady state approximation. So we last time talked about this mechanism, a simple mechanism, 2 steps, A going to I or intermediate I going to P, and there's 2-step mechanism here, right? And right, we solve for this exactly, okay, the concentrations of I, P, and A as a function of time. But now we can ask some questions about, well, what if there's kind of a difference between the rates of these 2 reactions, maybe significant difference, right? What if this first reaction, the rate constant is much larger than the second reaction, so it's going to be much, much faster? Or what if the second reaction, the rate constant's much larger, right? So if we imagine this, right, in the first reaction, if this is significantly faster than the second reaction, right, then basically I can imagine in extreme cases, right, I've reacted almost all A and formed I, and then I is just slowly decreasing its concentration as a function of time to form P. Okay. Which could be possible, could be happening, right? In the second case, if this reaction is significantly faster than the first, then what happens is basically my concentration of I is going to be very, very, very small as the reaction is going, because every time I form I through my slow reaction, that I quickly disappears to form product P. Okay, right? And so, here. Right, and so you can imagine, right, that in the second case, right, concentration of I is going to be relatively small and fairly constant over the course of your reaction, okay, which is kind of the typical thing to occur for an intermediate. Often in chemical reactions, right, your intermediate is not going to exist everywhere. Okay, your intermediate is right for the entire reaction, right, and you're not going to have a large amount of it, right. Typically, your intermediates can often be very unstable, right? Not something you can really isolate, and they're going to be typically at very low concentrations of the reactions going. And so often, right, the second case here, Kb being much greater than Ka, is typically the case that often in your chemical reactions you form the intermediates at some rate, but then those intermediates go on and do their reactions significantly faster than which they are formed, and so their concentration is typically very low and relatively unchanging as the reactions go. Okay? And so the steady state approximation, right, it is just saying that after your reaction's kind of started and some initial amount of your intermediate's been formed, that its concentration doesn't really change significantly as time is going on. So it stays relatively small and relatively constant throughout the entire reaction, okay? And mathematically, what that basically means is that we assume that the change in concentration of your intermediate with respect to time equals 0, okay? I don't know if you can see what I'm pointing to on the slides from my phone, but yeah, that's what it means, right? Is that the change in concentration of your intermediate as a function of time is equal to 0, okay? And that is the steady state approximation. That for all intermediates, their concentrations as a function of time do not change, okay? So you set those derivatives equal to 0. That allows you to simplify some of your rate laws, rate mechanisms, and things like that. And more importantly, make it so our final rate laws do not involve intermediates, okay? Right. So, right, let's see what that steady state approximation does to this simple mechanism, right? Again, the steady state approximation says the concentration of I does not change with time, okay? So if I write out what is the change in concentration of I with respect to time for this reaction, right? It's the rate of the of the first reaction, which has a rate law of Kaa, and then it's minus the rate of the second reaction because I is being consumed in the second reaction. And that rate law for that second reaction is KBI. So you get minus KBI. And all of that has to add up to give us 0, according to the steady state approximation, okay, which tells us, right, in the steady state approximation, the concentration of I is just approximately equal to Ka divided by Kb times concentration of A. Okay. Which again, the place where the steady state approximation is most valid is when Ka is much, much smaller than Kb, right? Kb being the rate of that second reaction is significantly faster than the rate of the first, right? And so in that case, this ratio Ka over Kb is a very small number. So a very small number times your concentration of A yields a very small number for the concentration of I, right? So again, we see that the steady state approximation is all about that the rate in which you form your intermediates is much slower than the rate in which they are consumed. Okay. Right. And so what does that mean in terms of kind of our concentration as a function of time? Well, right from that mechanism, right, our change in concentration of P as a function of time, which is KB times I, well, with the steady state approximation, we can plug in that concentration of I is just Ka divided by Ke times concentration of A. So plug that in, you get Ka times Kb times concentration of A divided by Kb. Kb's just cancel, right? You're just left with Ka times A, right? And then using, and so that's what the change in concentration of P is a function of time, just Ka times A. Using the integrated rate law for A, which is just from our first order kinetics problem, right? First order integrated rate law. Plugging that in and then integrating out, right? You'll find that the concentration of P as a function of time is just Ka times A naught times 1 minus e to the minus KAT, right? That basically, if you were to plot this, okay, right, let's imagine that we're going to plot. A purple chalk, just it was gray. All right, right. So let's kind of plot what this looks like, right? So basically, the steady state approximation is kind of saying, like, if we were to plot our concentrations versus time, right? You know, for all of this, right, the concentration of A is a function of time, is just some exponential decay, right? It's just concentration of A, right? And then in the limit, kind of where steady state approximation works, right? The concentration of the intermediate I, the idea is it just kind of this, you know, imagine just this flat line at a very small value, right? Concentration of I, okay? And so the concentration of I is, you know, very small and constant, not really changing, okay? So the concentration of P is basically just going to be kind of the inverse, right, of the concentration of A, right? That as A is decreasing, concentration of P is increasing at kind of the same rate, right? And that's what you get from that equation. That from, okay, you know, the equation on this slide, the concentration of P, right, increases at the same rate, right? Concentration of A decreases at a rate of e to the minus KAT. Well, concentration of P is just 1 minus that, which means, right, at time 0, this is 1 and that's 1, so this is 0, right? So this increases from 0 on up, right? So you get to the concentration of A at a rate of e to the minus KAT, right? So the concentration of P increases at the same rate the concentration of A decreases, right? And the only way that can occur is if your concentration of your intermediate I is very, very small and relatively. Question. Yeah.
So does the steady state approximation just kind of assume there's a fast step and a slow step, and the fast step just doesn't impact the rate, like, at all?
So that's kind of what happens in this situation. So kind of what you're getting at is sort of the rate determining step approximation and pre-Eclipse approximation, which that stuff you guys have maybe seen in Gen Chem. I know when I teach 1342, I talk about the rate determining step and pre-Eclipse approximation a little bit there. I don't really talk about the steady state, but I talk about those other ones. And so, yeah, so the steady state approximation, you know, can be used in relation to the rate determining step. But it doesn't always kind of work out like this, I guess, in terms of it looking like basically the first, you know, the rate of the first step is irrelevant or something like that, right? Yeah, that doesn't usually always work out that way. So other questions about kind of steady state approximation? Right, it's not going to be your job to determine is the steady state approximation valid or not. You'll be told use the steady state approximation or use pre-Euclid approximation or something else like that, right? You might be asked, with the steady state approximation, is the rate law that you get from a mechanism agreed with experimental values, right? But that doesn't necessarily mean that steady state approximation is bad. It might just mean your mechanism is bad, right? If it doesn't agree. But you're never going to be asked like, find this rate law and use the steady state approximation. Who knows, right? Like you're going to be told use the steady state approximation or use some other type of approximation. Okay? Right in this slide here, I'm just showing right the exact result compared to our approximate result. Our approximate result, right, is much simpler, easier to solve for. And that's why we use these approximations for more complicated mechanisms, right? And if you want, you can go through and do the math of when you set Ka to be very small compared to Kb, right? And kind of simplify this term here. You'll get the final expression up here: 1 minus e to the negative Ka times K. All right. Okay. So question here, right? We have a mechanism, right? And the question is, which one of the following relationships is assumed if the steady state approximation is valid? Okay. So your mechanism here, NO plus Br2 going to NO Br2, NO Br2 plus NO going to 2 NO Br. And again, if the steady state approximation is valid, what are we assuming? Are we assuming dNO dt is equal to 0, dBr2 dt equals 0, and dNO Br2 dt is equal to 0? C. Yeah. So it is going to be C here. Oh, is there something? Sorry. Yeah. So the chat, it's okay. C. So that's what I'm trying to see. All right. Fantastic. Yeah. So C here. Again, I apologize if you're not able to really see what's on the slides here from those on Zoom. Again, the questions are on the lecture slides that are posted, so you can always follow along there, right? But yeah, C here is what we use for the steady state approximation. Okay. Right. And so that same mechanism, basically the same question, but now answered in a different form, right? Which of these equations would you get from the steady state approximation, right? For this mechanism. Okay, so you have this mechanism, we apply the steady state approximation. Which of these equations is valid and works for that steady state approximation? Anyone? Here. Anyone have any thoughts? A, B, C, D, or E?
None of these.
Got some none of these. So the first thing we can look at, right, is in this reaction or in this mechanism, right, there are 3 reactions, right? Or let me step back from that even before, right? The very first thing, right, what is a steady state approximation? Well, we talked about in the previous question, right? It's when the change in concentration of NO-Br2 with respect to time is equal to 0, right? And so basically here, we're just writing out what is that change in concentration of NO-Br2 equal to, right? What is that dNO-Br2 dt equal to, right? And so the concentration of NO-Br2 changes from the 3 reactions it's involved in, right? the forward reaction in equilibrium, the reverse reaction, and the forward reaction in that second step, right? Which means I should have 3 terms appear in this equation, in this expression, okay? So we already know B and D are not going to work, right? And so it's either going to be A, C, or E. And then we just need to start kind of looking into which of these might work, right? So for the forward reaction, K1, right, NOBr2 is a product, so it should be a plus K1 NO times Br2. A here we have a minus K1 NOBr2, so that's not going to work. D or C, we do have a plus K1 NOBr2, so that's great. Okay. In the second reaction that's involved in like the reverse reaction of NOBr2 forming NOBr2, right? That rate law is K minus 1 NOBr2, but NOBr2 is a reactant in the reverse reaction. So it's being consumed, so its concentration will decrease based off the rate of that reaction. So it should be minus K minus 1 NOBr2, and here we have plus K minus 1 NOBr2. So that's also wrong, so it is E, none of these, okay? In C, the third term here, minus K2 NOBr2 NO is correct. So C is almost correct. It just needs a minus sign for that second term. It should be minus K minus 1 NOBr2. Just a note here, if ever, so when you're writing out, right, these rate laws, right, in terms of like rate constant times concentrations, okay? If one of the concentrations is the thing you're looking at, like d NOBr2 dt, right? Looking at the change of concentration of NOBr2 as a function of time. If that concentration appears in that rate law expression, okay, it's got to have a minus sign in front of it. Because if the concentration appears, that means it's a reactant, right? Because our rate laws for elementary reactions are just rate constants times concentrations of reactants. So it's got to be a reactant, and if it's a reactant, that means its concentration has got to be decreasing based off of the rate of this reaction, right? So if ever you see, you know, again, for this, we're looking at dNOBr2 dt. So wherever I see an NOBr2, I should have a minus sign in front of that term. Okay, so it should be a minus sign here. No NOBr2, okay, so that should have a plus sign, okay, right? So that's another kind of mental check you can do for yourself. Did I write this thing out correctly, okay, in terms of my plus signs and minus signs and things like that?
I have a question.
Yeah.
I have a question. On C, should it be negative 2K2, reflecting the 2 NOBr? Am I thinking about that?
No, so the 2 here, right, yeah, we have 2 NOBr. That factor of 2 will appear if I ask what is dNOBr dt. So what is the change in concentration of NOBr as a function of time? Well, in that case, its change of concentration is twice the rate of this second reaction because of the stoichiometric coefficient of 2. So dNOBr dt would equal 2 times K2 NO times Br2. That makes sense. I can try to write that out on the board.
No, that makes sense. Thank you.
Okay. Any other questions about this? So forward. Okay, I don't see any questions from the chat recently. All right. So, all right. So let's get into a mechanism here, but I'm applying the steady state approximation. So given the following mechanism, overall reaction 2N2O5 going to 4NO2 plus O2, what is dN2O5, right? The change in concentration of that reactant with respect to time, assuming a steady state approximation. Okay. And we'll note here, whenever you're asked for what is, typically you're asked for what is the rate law, but even in this case, when I ask what is dNO2O5 dt, okay, I don't want my final answer to include intermediates. Okay. You should never have your final answer for these things typically including intermediates, unless you're asked like, what is the multiple choice question about what is that we just did, right? In the previous slide, right, that multiple choice question, you're asked like, what is the steady state approximation, right? What is that telling you, right? Well, in that case, sure, intermediate concentrations can appear in there, and that's fine, right? But if you're asked for like, what is the rate of change in concentration of a reactant or product in your overall chemical reaction, or more often you're asked, what is the rate law of that chemical reaction? Well, you never want an intermediate to appear in the final answer. Products can, reactants of course can, the intermediates will not.
That N2O5 like rocket fuel additive?
Could be.
It's like a crazy volatile derivative of nitrous, right? So
Yeah, usually be. I mean, these rocket fuels and things like that are nitrogen based
yes.
compounds and things like that for sure. So definitely wouldn't be surprised. With that screen. All right, so let's go over this, and then let me move where the camera is real quick. So let's see this better. Just try to manual zoom here. Back to where we were, just focusing on this board on the right. Okay. So I have the equations written up here. Again, if you're on Zoom, I recommend using the slides if you can't really read what the heck's on the board here, right? So we have the three reactions, N2O5, going to blah, 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 NO2 plus NO3, and NO plus N2O5 going yada, yada, yada. Those three reactions, each reaction has a set of rate constants, Ka, K minus A, KB, KC, right? And so some of the things that we can first ask ourselves are, for example, what are the intermediates in this reaction here? NO3, NO are my intermediates. Okay. So if I'm using the steady state approximation, I'm going to be saying D NO3 dt equals 0, and D NO dt equals 0. Okay. So if I need to use those, that's my steady state approximation. But again, the question itself is just asking, what is DN2O5 equal to, right? ET, right? Well, if I want to know what that equals, let's just write it out, okay? So N2O5 appears in the first reaction, which has a forward and reverse reaction, right? And it appears in the third reaction. So there's going to be three terms here. And so I'm going to write this out as VA plus, or sorry, negative VA plus V minus A, right? N2O5 appears in the first reaction as a reactant. So it's going to be a negative times the rate of that first reaction, okay? V minus A, and then I'm going to do plus, or sorry, not plus, sorry, it's going to then be minus the C, right? The rate of that third reaction, okay? Right. Yeah, I'm zoomed in here, but at the same time, want more board space. So let me write out, right, just real quick, what VA, V minus A, VC, and then I'll do VB, right? So VA, right, the rate law for that first reaction is just Ka times concentration of N2O5, right? V minus A is just K minus A, concentration of NO2 times concentration of NO3. VB, just writing all these out, right, is going to be KB times concentration of NO2 times concentration of NO3. Okay. And then finally, VC is KC times concentration of NO times concentration of N2O5. Okay. So again, and so I'm writing things out in terms of like minus VA, V minus A, and VC and things like that to make life a little bit simpler, right? Because you notice, right, that both V minus A and VC, okay, both of those have intermediates, NO3 and NO, appearing in those expressions. So I need to get rid of them, right? To get rid of those intermediates, I got to use the steady state approximation, okay? So the steady state approximation, right, is dNO3 dt equals 0 and dNO dt equals 0, right? And so if I want to write out, right, what is d, say, NO dt, okay, in terms of these rates, V's, VA, VB, and so on and so forth, right? Well, NO appears in the second reaction, okay, VB, as a product, and then it appears as a reactant in the third reaction, VC. So it's just VB minus VC, okay? And that equals 0, okay? And then dNO3 dt, right? NO3 appears in first equilibrium reaction and the second reaction. Okay, so it's VA minus V minus A minus VB. Okay. Right. So again, the change of concentration of NO3 as a function of time is VA minus V minus A and then minus VB, right? Because NO3 is a product in the forward reaction under equilibrium. It's a reactant in the reverse reaction, and then it's a reactant in the forward reaction for the second reaction, KB here. Okay, and then that again equals 0, right? And so, we can use some of this stuff to potentially simplify things if we want to. Right, so I write things out like this to kind of see some stuff. So, but basically, right, what we have is we have these two equations that have two unknowns, right? My unknowns are the concentration of NO3 and the concentration of NO. I want to solve for what the concentration of NO and NO3 are in terms of reactants and products. Okay, so this is all like this class, and for the rest of kinetics, basically, this is what we're doing. Okay, this lovely stuff. Okay, we're writing out a bunch of equations, and it's doing a bunch of algebra. I got a bunch of unknowns, I got a bunch of equations, and so I use those equations to solve for my unknowns. Okay, and so there's a lot of ways, right, that you can do that. We're given sets of equations, right, and set of unknowns, right. There's a lot of ways you can manipulate those equations and do things to solve for what you need to solve for. And so I like to write things out how I've done it here in order to try to maybe simplify things down in some way, right? Because what I can see, for example, from the very first steady state approximation, I can see what that's telling me, right, is that VB equals VC. From the very first steady state approximation, the rate of the second and the third reaction have to equal each other, okay? So what that steady state approximation happens to say, right? Right. Yeah. And so, right, and the third, right, and then the other steady state approximation, right, can potentially tell me something. I'm trying to think of ways I can manipulate this, right? Because basically, if I could get everything in terms of just VA, then VA is the only one here that doesn't depend on an intermediate, right? VA minus, VB, and VC, all those rate laws depend on concentration of intermediates, but VA is the only one that doesn't. So let's see here, right? So this second steady state approximation here, VA minus V minus A minus VB equaling 0, tells me that V, A equals V minus A plus VB, right? Which doesn't quite help me, I think, from above, right? Because what? V minus A plus VB, right? Because again, there's different ways to try to solve this. Just trying to think. I'm going to erase the reactions because we don't really need those anymore. Okay. Right. So I'm just trying to see if before plugging in for the rate laws, if there's any simplifications we can do, right? So again, we have D N2O5 DT. Do any of these relationships help me out in simplifying that, right? Right, I have a minus, pull that out, right? I have something like V, VA minus V minus A plus VC, which again, I can use VC equals VB to say write that as VB, right? But then I have VB minus VA, which isn't quite the same thing as V minus A plus VB, right? So I can't plug this in up above to just get my DNO2 DT in terms of say something like VA. So sometimes you can use these relationships, writing it like this, and basically get rid of your intermediates right away and get this final simplified answer without having to plug in a bunch of crap. Okay, so that's why I was doing this, to see if there's a simpler way we can do this. There isn't one. Okay, right. So we're gonna have to kind of plug in things to get to what we need, right? And so let's now plug in for kind of these steady state approximations, right? So VB equaling VC, right? That the DNO dt equaling 0, right? From that one, I get K minus A times NO2 times NO3 equals, oh, no, shoot. I needed to do KB, KB times NO2, NO3, right, equals KC times NO times N2O5, okay? Or again, if I want to write the steady state approximation as is, right, set that equal to 0, okay? And then the other steady state approximation, right, KA, 0, right, times N2O5 minus B minus A, so K minus A and O2 times NO3, okay, and then minus VB, so minus AB and O2 and O3. Okay. So the thing is right, NO3 and NO appear in both of these equations. Okay. There's no easy way to get rid of. Well, actually, the second steady state approximation, d NO3 dt equaling 0, NO does not appear in this expression, right? If I wrote it out correctly, which I think I did, right? And so I can use that to solve for what the concentration of NO3 is in terms of the concentration of NO2 and N2O5, okay? So I'm going to pull out a factor of NO3 here. So we're going to have Ka times N2O5 minus concentration of NO3, which is our intermediate, times K minus A and O2. Actually, I can full factor out a concentration of NO2 as well. So concentration of NO3, concentration of NO2 times K minus A plus AB. Okay. And that equals 0. And so solving for NO3, you get the concentration of NO3 is equal to Ka N2O5 over NO2 times K minus A plus AB. Okay. So here we now have concentration of our intermediate NO3 in terms of concentrations of reactants and products. Okay.
Can we see that side a little bit better?
Like that. Let's see here. Let's see if I can. That again, I apologize. So small. If you're on the slides, so on the slides, this is also kind of written out on the slides. Let's see here. So you have the question. Oh, let me go back here. Right. So there's the question slide when the question's initially posed. Right. Given the following mechanism, blah blah blah. You go forward 1, 2, 3 slides. Okay. You'll have, from this last slide, written out the steady state approximations for NO3 and NO at the top of the slide. And then solving these equations for NO and NO3, we have below, right? And so I've just solved for the concentration of NO3, okay, in terms of N2O5 and NO2, right? And then what I can do is plug that in to the above equation up top here. Okay, KB, NO2, NO3, right? I can set these things equal to each other, right? I want to rewrite it like that, right? So I have, right, concentration of NO in terms of NO2, NO3, and N2O5, right? And so taking this equation up top, okay, and just rewriting it a little bit, okay, you have concentration of NO equal Kb over Kc times concentration of NO3 times NO2 all over N2O5, right? Which I can then plug in what the concentration of NO3 is into this equation up top, okay? Find out what the concentration of NO is in terms of other things, okay? Right? And so when we plug that in, right? So plugging in NO3 is equal to NO2 divided by NO. You'll see, I'm sorry, NO3 is N2O5 divided by NO2. Okay, plug that into here. The N2O5s cancel, the NO2s cancel. Okay. Right. And when you plug in that, you'll get concentration of NO is equal to Kb, Ka divided by Kc times K minus A plus Kb. And that's it. So you get the concentration of NO actually is just equal to a bunch of rate constants. Okay. Which again is on the lecture slides, plugging that in, solving for that. Right. And so now I can take these two equations and plug them back into my initial expression for what is the concentration of N2O5 as a function of time, right? Or what is the change of concentration of N2O5 as a function of time, right? Plugging in for V minus A and VC here in terms of NO3 and NO, okay? And when you plug that in, why don't I just go to the slide here? I don't know. Yeah, again, I apologize that how we're having to do this lecture, but we'll do lots more examples of this stuff on Wednesday, and things should hopefully be back to normal then. But basically, when you plug in, slides here, right? So plugging in for those two things into what the expression is for dN2O5 dt. Okay. So plugging in for NO3 is here, right? What you see here for NO3, you're dividing by NO2, so the NO2s cancel, and you're left with the concentration of N2O5 with these rate constants here. And then you have this expression here, okay, where when you plug in for NO, which is just a bunch of rate constants, you get then just a bunch of other rate constants here, okay. And then to simplify this, you find your common denominators, which is K minus A, KB, or K minus A plus KB. So you multiply this term here by K minus A times KB, okay, on top and bottom, and simplify things. And what you'll get is the K minus A terms will cancel each other, and basically you're left with this final expression here. That the change in concentration of N2O5 with respect to time just minus 2 KB Ka divided by K minus A plus KB times concentration of N2O5, right? And so you see, right, that for this mechanism that we had, which was essentially the decomposition, right? Overall chemical reaction was two what was it, 2N2O5 forming a bunch of stuff. Let me go back real quick to the overall chemical reaction, right? Overall chemical reaction, yeah, was 2N2O5 forming 4NO2 plus O2 gas, right? So for the overall chemical reaction, we see that the rate law, right, is essentially going to be first order with respect to N2O5, right? Then this ends up being a first order kind of decay rate, assuming the steady state approximation is valid, right? It's just the rate constant for that first order decay is some combination of rate constants from a bunch of different reactions, okay? The overall order of that reaction ends up being first order with respect to N2O5, okay? Given that mechanism, right? So assuming that mechanism is true, the steady state approximation is valid, right? Then experimentally, you should measure, right? If you were to measure what the rate law is for this reaction experimentally, right, you should get that it will be first order with respect to N2O5, assuming your mechanism and steady state approximation are valid. And so again, this is the type of problem that we need to do. We'll do more examples of just these general chemical reactions, but then we'll apply kind of these steady state approximations and other approximations to other chemical reactions, more specific things like polymerization reactions, photochemistry, enzyme kinetics, and that type of stuff. Okay, in order to kind of see what these mechanisms are, what the type of rate laws they show to be, and things of that nature, right? But again, this is something that you potentially would do in lab, right? You'd say, okay, this is the mechanism I think my reaction has, right? What is the rate law for that mechanism that I would expect? And then I'd measure that rate law and see if they agree. Okay. Right. So some questions about this example. Now, I know it wasn't the best to follow along. I was trying to kind of, when doing it by hand, use just one side, one half of the chalkboard space, and things like that. And yeah, it would hopefully be easier to follow along when able to use kind of the computer on Zoom and share screen.
Just going from the second to the blue line, or the bottom line. In other words, yeah, that's the second one up.
Yeah.
In the middle is where that KB comes from. Is that correct? Because I see the negative KA in the first term, and then in the third term, I see the negative KA.
Well, so what happens is I have to find the common denominator. So I got to multiply this term by K minus A plus KB on the numerator and the denominator. And so in the numerator, right, I end up getting K minus A times KA with a minus sign, and then I have K minus A with a plus sign, so those cancel with each other. And so that term goes away, and I just left with twice the amount of these terms.
For some reason, I just thought like there was some unsaid thing of like KA times K minus A is equal to KB in this situation. So
yeah,
I see it's just a common denominator. No problem.
Yep. Right. And the key kind of take home from this example, right, is just at least setting up these equations and things like that. If you're not super comfortable solving for them right away, hopefully, you get a little bit more comfortable as you do more and more examples in slides and in class. But, and on homework. But yeah, but at least setting it up, hopefully, right, setting up what are these equations, right, go back, okay, right. What is the steady state approximation saying and things like that, right? Just setting up kind of this stuff here is kind of hopefully where we are at. Able to do with some level. So with that kind of ends what we have time for today. So we'll do some more examples. We'll go through this lovely mechanism on Wednesday. And again, try to, so this one on the slides, I think I have some complicated crap to do to get the final answer. We might have to do it that way, I don't know, but yeah, this has some lovely final answers with half, square roots and then 3/2 roots of powers and things like that. So, So we'll do some other complicated examples and things like that, go through them. And again, hopefully we can do it a little bit better fashion for those who are online, and even for those who are in class here, since I kind of was cramming on half of it to try to make things work as best as possible for online. But yeah. So, and remember, your homework is due Wednesday. If you don't see some sort of like online homework one thing appear kind of in your assignments that has the ability to submit something, shoot me an email. If you've done so already and I haven't added you to the list of online students, I apologize. If you want to send me another email to remind me, please do so. But yeah, otherwise just shoot me an email and let me know, hey, I'd like to submit this online. So you can do so. But again, it's going to be due at the end of the class period on Wednesday. So the next time we meet. Okay. Otherwise, yeah, that will be it for today, and I'll see you guys Wednesday. And again, I apologize for the kind of crappy version on Zoom here, but
I don't think it's your fault. Thank you.
all right. So I'll see you guys later.